Thank you very much for the invitation. Thank you very much for the organizing committee for this very nice opportunity to be in Grenoble. So I will talk about axisymmetric perturbations of Kerr, and of course, this will be remarks in the sense that this is a very difficult problem, as I will try to explain, and I will only be able to talk about some small progress on the problem. So let me start with recalling what the conjecture is. This will be discussed by Michalis. So here is a diagram of the Kerr solution. This is the inside of the black hole. This is the external part of the Kerr space-time. And the conjecture says that small perturbations, so the perturbations you think of making them on a space-like hypersurface, like for example, imagine a small perturbation somewhere here, will lead to a space-time which has its maximal future development converging to another Kerr solution. So again, this was mentioned by Michalis, that you don't expect the final solution to be the same Kerr. In other words, to have the same parameters. So they A and M will have to change. So what are the difficulties of the problem? First of all, the gauge covariance I would take as being the main problem. It's linearization. So as we all know, a problem, somehow you have to linearize, even though often the linearization may be just conceptual. Not necessary. You don't necessarily have to do it. There is something that we call conceptual linearization, which means that somehow you point out what are the main variables and you treat them in a way by linear theory. Now, of course, linearization, however, has a lot to do with gauge covariance because obviously, if you take a nonlinear problem, you make a nonlinear transformation, you linearize, you get a completely different linearization than the one of the equations you started with. So this is a very serious issue, and of course, linearization is used in this nonlinear problem in order to get decay estimates and robust boundedness of the solution. So this is what I call the issue of proper linearization. Now, I should say, maybe in this context, I want to point a little bit what is the relationship between an L2 bound and an L infinity bound, because you see here that I mentioned both of them. So the thing to have in mind is, say, the kind of problem which was mentioned yesterday by Vasi. You have a quasi-linear equation, say. And here you have a nonlinear term which depends on phi and, say, a derivative of phi, let's say quadratic. That's a sort of a typical model equation, which has a lot to do with dimensional equations written in wave gauge, in wave coordinates, I should say. So the kind of the fundamental estimate that allows you to prove, say, global existence for small data will be one in which you estimate the HS norm of derivatives of phi, let's say at time t. So imagine that you have a foliation, sigma t foliation, so time t. You estimate it in terms of initial data at time 0 times an exponential. So this is a typical Gronwall inequality, exponential of an integral, say, from 0 is your initial, the starting point, to t. And here you have the L infinity norm, typically L infinity norm of phi. So you need the decay estimates in order to control this. Okay. Now, of course, you only get decay like t to the minus 1 if you're in Minkowski space, which means that this is divergent. So that's why you need the null condition. But anyway, I don't want to get into this. All I want to say is that there are a small number of derivatives that need to be estimated with decay. Right? So in other words, S can be very large here. This will be just one derivative of phi. So therefore, if you lose derivatives in sup norm when you try to prove decay, then it's not going to affect very much the main argument of proving global existence or proving the stability. So that's sort of a remark to what was discussed yesterday by Vasi. Somehow the loss of decay, the loss of derivative when you prove decay does not seem to be so important. And for that reason, we don't believe that you should use Nash-Moser. Okay? But anyway, this is just a sort of a small remark. All right, so let me go on. So you can do linearizations at different levels. For example, you can do a linearization at metric coefficients. This is what's done when you introduce wave coordinates and you write down the Einstein equation. In fact, as a system of equations looks very much like this. This was used, of course, as we all know, in the local existence result of Yvon Choquet-Brouat. You can also use connection coefficients. This was actually used in the bounded L2 curvature conjecture, and Jeremy is going to talk about this. Okay, so you can also work at the level of curvature, and of course in the stability of the Minkowski space. That's what Christodoulou and I did. We used somehow the linearization was done at the level of the Riemann curvature tensor. So the conceptual linearization. There was never a linearization being implemented, but there was a conceptual linearization, which you always have to keep in mind here. Of course, the problem is quasi-linear, and because of this, there are many, many difficulties, in particular the fact that the characteristics of the problems are non-trivial. They depend on the solution. And also, you need a null structure. Already I mentioned, if you just use an estimate like this, you will be stuck because this is divergent, and you'll never be able to prove stability. So in order to do the stability of Minkowski space, we have to take into account the specific null structure of the Einstein equations, which was understood at the level, again, at the level of curvature. Now, if you go to Kerr, so if you compare the Einstein equation, so I should say, maybe I'll make another remark, another small detour here, and say that for the Einstein equation, in proving the stability of the Minkowski space, we use curvature. In fact, we used the Bianchi identities. So let me write schematically dr equal to 0. So this will be the Bianchi identity satisfied by the Riemann curvature tensor. And what's very, very important in all this, that somehow in the nonlinear problem, you have things which depend, well, it's much more complicated than this, but anyway, it will depend, let's say, sort of very roughly, it depends on curvature squared, which will be a small quantity here. So if the curvature, you expect the final curvature to be small, and this is quadratic in the curvature, then somehow the scheme works very well. Now, in the case of Kerr, if you do the same thing with Kerr, this will not be true. You have other terms here when you linearize. You'll have other terms, and therefore the simpler structure here. By the way, you also have to think of the simple structure in Minkowski space. So you can linearize somehow the covariant derivative of curvature in Minkowski space. So this would be sort of the simplest possible way to do this conceptual linearization I mentioned about. And now, once you are in Minkowski space, these equations, we know how to treat these kind of Bianchi type equations. We know how to treat by L2 estimates and vector field method. Now, if you are in Kerr, this is much more complicated because you don't expect that simple linearization to hold true. Okay, so we'll talk more about this in a second. And then, of course, there are many other issues like limited symmetries, presence of the ergo region, which we heard a lot about it, and of course the presence of trapped null geodesic. Finally, there is the issue of modulation in the sense that the final state of the solution, as I mentioned, is not the one that you started with, so you have to also take that into account. All right, so what are the main results we have today on stability? Of course, the only global stability result, fully nonlinear, is the stability of Minkowski space. Of course, Minkowski space is just the trivial solution of the Einstein equations. There are no black holes, and it's obviously much simpler. And I mentioned already that the main point is somehow to do this conceptual linearization of the Einstein equations when you do a stability of Minkowski space at the level of the Bianchi identities, and then treat these Bianchi identities, and then somehow close the result. Okay, so the next, say, result that, I mean, there were many results in the physics literature, of course, but I'll mention just this Whiting result, which is mode stability of the Kerr family result, which shows that there are no exponentially growing modes. And this is a result that, if I understand correctly, was also used in the recent results by Dafersmo and Rodniansky. Okay, so then there is a stability for scalar linear waves, meaning that you look at a very special equation. You don't look at this Bianchi identities, but rather you just take the ambition of phi. So this is a wave operator applied to phi equal to 0 relative to the Kerr metric. Okay, so that's sort of what Michalis likes to call the Poor's main linearization. But it's a beautiful, it's really a beautiful model problem for understanding linear theory, because you have to deal already with the issues of ergo origin and trapping. So, and of course, there have been a huge amount. There was a burst of activity in the last 10 years, and all the names have been already mentioned. So I'm not going to say anything more than that. There is this beautiful result of Daferman, Holzegen, and Rodniansky, which is a nonlinear result for the Einstein equation. So it's actually a construction of a dynamical black hole starting from infinity. So again, was mentioned by Michalis, so I'm not going to spend any more time on this. And then, of course, the final result in this series is this new result of Dafermos, Rodniansky, and Schlappentock-Rothman, where you have stability for scalar linear waves for all values of A. So these were for small values of A. This is for all values of A up to M. Right, so that's a situation. Now, let me go to stability of Minkowski space. So I already mentioned that one of the main ideas is to look at this type of equations in Minkowski space. Okay, so imagine that D is a covariant derivative in Minkowski space. W is a tensor which has all the symmetries of the Riemann curvature tensor and Ricci free and traceless. So in other words, this is also traceless in the same way that the Riemann curvature tensor will be traceless for the Einstein vacuum equations. And then perturbation radiate and decay sufficiently fast. So again, decaying sufficiently fast, one should always have in mind this simple model problem here. You will always have a component of the curvature which does not decay any better than a solution of the wave equation in Minkowski space in that case, right? So you'll always have something which will be a t to the minus 1. So therefore, you have to worry about, and you have to do a lot of work in order to avoid that kind of logarithmic singularity. And of course, you have to have also an approach to proving in L infinity estimates. How do you prove L infinity estimates? You can use Fourier transform, you can use fundamental solution, you can do, I don't know, you can do the sort of things that we heard yesterday from people using scattering theory techniques. But the one thing that certainly worked for us in the stability of Minkowski space is actually to get the information about decay using vector fields. Okay? The reason is that you want to, the vector field then can be tied together with the energy estimates. And somehow you close everything just at the level of energy estimates, which are very robust. So this is one of the important techniques that you have to use vector field methods to get decay. Generalized energy estimates, well, these are tied to the vector field approach for decay. As I said, you get everything from generalized energy estimates. In other words, energy estimates where you involve this special vector field. The null condition, I mentioned it earlier. And last but not least, it's sort of a way, and I think this is one, I would think this is one of the main advances in nonlinear PDEs in the last 30 or 40 years, the ability to do very complex bootstrap arguments. So you have an enormously complicated problem with lots of things going on at the same time. And somehow you have to simplify by making certain assumptions. Of course, you have to make clever assumptions and then show that these assumptions are verified later on. Okay? In fact, you always start with some assumptions and then you do better. And finally, also, I should mention access to simple model problem. I mean, one of the things that worked for us in the stability of Minkowski space is because we understood very well the simpler case of the scalar wave, quasi-linear scalar wave equation. Okay? All right, so let's go on. Again, the same conjecture. So what I want to talk about is our intermediate. So this is clearly a hugely difficult problem. And though there was a lot of progress made for this poor man's linearization, which I think are extremely substantial. And in fact, they are the reason why we can start now making progress on the nonlinear problem. There are still, I think, the goal is still far away. And sort of what I became involved with is to look at axially symmetric perturbations. And I'll try to discuss why axially perturbations are somewhat simpler. And there are two types of cases that should be interesting to study. In fact, I'm involved with two projects. One with Jeremy here, the polarized case, and another one with Alex Ionescu, which I call partial linearization. And in fact, I'm going to talk mostly about this partial linearization, where we can now at least record some progress. So let me tell you what axial symmetry does for you. So if you have axial symmetry, that means you have a Koenig vector field, which I call Z. Okay, so this is your Koenig vector field, and you introduce there is a well-known procedure of reduction based on the existence of this vector field. So what you do is you introduce the N's potential. There is a real part of the N's potential, which I call, which is obtained by just taking the metric evaluated at Z, and a complex part, which I'm not going to write it down for a moment. And then you put them together, say x plus iy, for example. You can look at the complex N's potential, and you get an equation which looks like this. So x times the dimension of g of phi is d mu phi, d mu phi. So you see, you get a very simple wave equation. Of course, it's degenerate because x is this g of z degenerates on the axis of symmetry of z. Okay? And that's one of the reasons why, I don't know, maybe people were a little intimidated about this kind of degeneracies. But it turns out that it's not so bad, as we shall see. Anyway, now once you have this, you can proceed with your reduction. And I'm not going to say exactly how it's done, but I'll say that essentially what you achieve by the reduction is that you split your metric G into this N's potential, this complex N's potential, which has two components, and the 2 plus 1 metric, which is a Lorentz 2 plus 1 metric. Right? So this is phi. And now you can look at the Ricci curvature of the metric H. Right? So the metric H is now 2 plus 1. So you have Ricci of H is d alpha of phi, d beta of phi. Okay, so you see it's coupled with the phi, and phi verifies this, the same kind of wave equations that we saw there. So it's a wave map. In fact, you can view this as a wave map from the space N with a metric H to the hyperbolic space, to the standard hyperbolic space, right? Poincaré, with a Poincaré, in the Poincaré formulation. Once you can solve this problem, you can reconstruct the space-time metric in this fashion. So this will be the full space-time metric, where these omegas here are obtained by solving this system. Okay, so it's a divergence curl type system, which you can solve exactly. And then you have reconstructed the metric, and you are done. Okay, so that's. So what is the advantage of this? I mean, you know, one of the great difficulties of the full problem is that it's very hard to separate the degrees of freedom, the true degrees of freedom of the equations from the non, let's say, all the other components, which are, in a sense, should be connected with a dynamical variables by complicated relationships, in particular by taking gauge conditions and so on and so forth. So here, the great advantage is that you have already a wave equation. So the dynamical degrees of freedom are only here, while this one is a 2 plus 1 metric. It's a Ricci curvature 2 plus 1 metric. As we all know, in 2 plus 1, the Ricci curvature determines the full Riemann curvature tensor. So in a sense, you could say that somehow you have separated the degrees of freedom. This is a little bit misleading because there are many other complications, but in any case, at least at first glance, it seems like you have achieved this. Now, okay, so that's what it is. So now here are two model problems that you can immediately discuss. So first of all, here are the model problem number 1, which I call partial linearization. So what you do is you assume that the metric, so you look at the wave map exactly as before. You have a wave map x and y, and you linearize the metric to be the space-time metric. So this is a Kerr metric. So you're looking at Kerr here, x and y, and you are looking at the perturbation of A, B, which is exactly the Nth potential of the Kerr metric. Okay. So this is, of course, this is a solution of the system. It's a stationary solution. So now what you have to do is to perturb a stationary solution of the wave map problem. Okay. So it's a partial linearization because you are looking only at let's say half of the metric, and you treat the other half by a trivial linearization. Okay. But what's interesting is that you get a wave map equation and you get a solution which is a stationary solution, and you want to do stability around that stationary solution. Model problem number 2, you like to prove stability of Kerr among axially symmetric and polarized perturbations. Yeah, so what that means is that you look at the system. Actually, you look at the system where you don't do this linearization. So you look at the full nonlinear equation, but you observe immediately that y, if you take y equals 0, this will be preserved. Right? So you can look, in other words, you can simplify this wave map equation quite a lot by taking y to be 0. Okay? So this corresponds roughly, this corresponds to perturbation of Schwarzschild, which was also mentioned by Michalis. Perturbation of Schwarzschild when you start up with initial data with 0 angular momentum. So it's essentially equivalent to that. Right, so these are two simple model problems, and of course, Michalis also talked about it, and they have, he together with Rodniansky and Holzegger have a program and have already achieved remarkable results, which he mentioned about this linearization. And the sort of thing that we do are slightly different, and we hope that somehow the two different methods will shed some light on this problem. Anyway, so let me I'll talk, in what follows, I'll talk mainly about problem number 1. All right, so again, as I said, you have a wave map. So it will be a wave map now defined from the Kerr spacetime with values in hyperbolic space. So that's where this is. And you have a special solution of it, which is exactly the Nth potential of the corresponding metric, which verifies the system, and you want to perturb around it. All right, so let's look a little bit in more detail. So here is a Kerr-Familin Bohr link with coordinates, which you all know and love. Now you can see what the Nth potential looks like in this case, right? So here it is. It's A is the sigma squared sine squared divided by q squared, and B is even more complicated. So you see that A and B is a stationary solution of that wave map, but it's a very complicated stationary solution. Okay. So here it is. Again, this is A and B verifies the system. Right. So the conjecture we have for modern problem 1 is that the stationary wave map phi naught is AB is stable under general axially symmetric perturbations of the wave map system. Okay. So this is for all values of A. I mean, the conjecture is for all values of A, but as you'll see, we only have some results for small values of A. Actually, we have one result, which is maybe the most important one, which is true for all values of A less than M. But the second result is more restricted. In any case, here is again, more precisely, given smooth initial condition phi 0, x 0, y 0, sufficiently close to this, on a space-like hypersurface sigma 0, there exists a global solution x and y such that phi is equal to phi 0 on the axis of symmetry, and phi converges asymptotically to phi 0. Okay? Now, remark that there is no modulation here. I mean, this is a true stable solution. Right? So the stationary solution is supposed to be stable entirely, and I'll give arguments for that. All right, so here it is again. The problem now linearized. So what the linearizations we do is we take phi to be AB, so this pair AB. Phi, so there should be psi here actually. This should be psi. So psi is this AB plus epsilon A phi A psi. Oh yeah, no, right. So sorry, this is a perturbation, right? So phi is the original phi. Sorry, excuse me. So phi is the original phi, and you take the stationary solution and you add the perturbation. But you see, you add the perturbation by putting an A in front of phi and an A in front of psi. This is because of the axial symmetry, because you want to you have to worry about the axis of symmetry, and this is how it looks, right? So you take initial data on sigma 0, and you want to do something about solutions in this case. There is a simple problem you can analyze first, which is the case when A equal to 0 and B equal to 0, where this linearization simplifies quite a bit. But in general, you see the linear equations are kind of complicated, and you cannot reduce them to the standard wave equations as you had here. Okay, so that's what the nonlinearity looks like. If you care about, I mean, let's maybe not worry too much about this now. And you have to show that everything is defined. I mean, so everything is well defined if psi vanishes on the axis. So you need a boundary condition for psi on the axis of symmetry in order to make sense of the nonlinear, or to make sense of the whole thing. And it's very easy to see, for example, that the null condition will be satisfied. So this is not an issue, right? So that's not the difficulty. Once again, as in the case of this equation, is what happens near the trapping region. Okay, so this is the goal, to establish a realistic bounds, including adequate decay for our system. And of course, I want to make a small comparison with a case that is now well understood, which is a wave equation in Kerr. So in that case, as we all know, there is an ergo region in which the time-like vector, Killing vector, the Killing vector field, which corresponds to time translation, becomes space-like. And there is, of course, a trapping region, which is a complicated trapping region in general. And of course, you have degeneracy of the horizon. That's taken care by the redshift effect, as was as well discussed by Michalis. You have the degeneracies of all your estimates due to trapping null geodesics, asymptotic region that you have to worry about. Anyway, so all these things are very well known now. So let me go now to wave equation in Kerr. I mean, sorry, what am I saying? Yeah, so I want to, excuse me, I'm still at this simplified linearization. But I want to look at the simplifications which are obtained in when you have when you assume that phi is also axisymmetric. So remember that everything we do is in the context of axisymmetry. So it makes sense to compare the results known here in the axisymmetric case. So the remark is that if phi is axisymmetric, there are two major simplifications. First of all, the ergo region problem disappears. And it disappears for some very simple reason. That is because since z of phi is equal to 0, then if you look at the energy momentum tensor of the wave equation, it verifies the simple properties that q of z and x is equal to 0 for every x perpendicular to z. And then also the fact that at every point, sorry, in the exterior region, there exists a time-like linear combination of t and z. And if you combine these two, and you also combine with the fact that you can integrate on z-invariant domains, you see immediately that you get a good energy degenerate only on the horizon, but there is no ergo region anymore. Okay, so that's a major simplification because you don't have to worry about the ergo region. Another major simplification is that the trapping is also concentrated on just one hypersurface, R equal R star, which is similar to what happens in Schwarzschild. In Schwarzschild, you have everything concentrated at R equal to 3m. Here you have everything concentrated at a value of R, which is a root of this cubic equation. Okay? So it's a largest value of R, which is, yes? So all the trapping is just like in Schwarzschild. In Schwarzschild, the trapping is at r equals 3m. So now it's, yeah. All right. So these are things that obviously are going to be very important for what we do. All right, so now what are the challenges of our problem? So first of all, you need quantitative decay estimates for the linearized equations. So when I say quantitative decay estimates, I should also add, of course, and boundedness, right? Boundedness of some type of energy. Okay, so this in particular, it's written here. You need a coercive global conserved quantity, like an energy type of norm. You need the control of the degeneracy of the horizon by an appropriate redshift mechanism, Moravec's estimate, and so on and so forth. Okay, so all these things here are made easy somehow by the fact that you are in axisymmetry. But the major problem is this one. Do you have an energy quantity? Okay? Because as you see, the linearized equations are much more complicated than the case here. So a priori, it's not at all clear that you have one. Okay, so you need to accomplish A, B, C, D, despite the fact that the linearized equations are by no means standard. You need to control also the degeneracy on the axis of symmetry. So that's where sine square of theta is equal to 0. And you have to, of course, to take into account the structure of nonlinear terms. So the main supporting evidence for the conjecture, which I have, is this result with Ionescu, which says the following: the linearized equations, so these complicated linearized equations that we saw, admit an energy momentum tensor type quantity Q, which depends on phi m psi and A and B. So A and B are the stationary solution. So it's a complicated energy momentum tensor, and the source J, which also depends on these two, such that Q verifies the following condition. First of all, Q verifies the energy condition. So this is exactly like the Q for the wave equation. You have Q of x and y is positive for every x and y time like future oriented. The second condition is a divergence of Q is equal to J. Now, this is sort of the major difference between this and this. In this case, J will be 0. So there is no source here. You have divergence of Q equal to 0. Here you have a source. And of course, once you have a source, this looks like it's not going to be very useful at all because the source is very complicated. And there's no reason why you have a source to have a good energy, for example. So the most important observation here is a third one, is that J is orthogonal to T. In other words, you can write down an energy momentum tensor which verifies this relation, which is with a source which is orthogonal to T. Therefore, when you look at the usual way to define an energy quantity, you multiply Q by T, and you look at the divergence of Q dot T, you will see that the right-hand side will disappear because of that condition. Okay, so that gives you an energy quantity. Because of this because of this condition, which is also true, it also follows that T, which is a time-like kinetic vector field of Kerr, will provide you with a good energy for the problem. By the way, this is also highly non-trivial, and it's the reason you have this positivity is because of the nature of hyperbolic space of the wave map. So you have a wave map from Kerr to hyperbolic space. The fact that it's hyperbolic space is extremely important, right? So it's something that has to do with a negative curvature of hyperbolic space. All right, so corollary, the existence of a coercive energy conservation law. And this, by the way, this holds true in all situations. So this is not restricted to small a. So here is the energy momentum. Now, the way to find the energy momentum tensor, you have to be somewhat clever. But in the end, once you have it, you can just display it. And that's what I'm going to do. So you display it like this. So d nu q mu nu is equal to j nu. Q mu nu is constructed like this. It's a tensor T, which is this one, minus a half g mu nu times trace T. And this E, F, and M, which appear here, are defined like this. So this is d mu of I plus psi A minus 1 d mu of B, and so on and so forth. So you see, it's somewhat complicated. But once you have it, you can just check that d nu q mu nu is j nu. You calculate the g nu, you find this. And you see immediately that if I take T times J, you get T times T applied to B. But that's 0 because B is stationary. And also you get T applied to A, which is also 0 because it's stationary, okay? So that's the reason why it works. The positivity, once you have the energy momentum tensor expressed like this, the positivity is an immediate consequence. It's very easy to see from the structure that you have positivity. All right, so now I want to talk a little bit about the Moravec type estimates, so the local decay estimates, which are also going to be a problem. Maybe I'll mention now. You see, typically, if J is equal to 0, the way, the classical way of getting decay estimates, the local decay estimates, is by using other type of vector fields. You don't use d over dt. You use, say, d over dr times a function of r. But once you do that, this source is not 0 anymore. So the source will play a major role. Okay? So you really have to redo everything that was done. In the case of the simple wave equation, you have to do it in this case. So anyway, here is something I want to mention about what we know in Minkowski space. So if I look at the wave equation in Minkowski space, there is a well-known estimate based on Moravec vector field. There are two Moravec vector fields that you have to always keep in mind. One is f of r d over dr, which is used in the local decay estimate. And there is another one, which people now try to avoid for obvious reasons, and I'll explain in a second, which is this one. And if you use this vector field together with the usual energy estimates for this equation, you get an outgoing, you go what I call the outgoing energy. So it's an integral of phi outgoing, which involves only L of phi, angular derivative of phi, and this term r to the minus 2 phi squared. So let me recall what these are. So L, so I'm in Minkowski space, right? So I'm in R1 plus 3. So L is dt plus dr. And of course, angular derivatives are angular derivatives relative to theta and phi if I'm in polar coordinates, right? Okay, so this expression you can show by using this Moravec vector field that it decays like O of t to the minus 2. Okay? So it decays like t to the minus 2. So this is a sort of thing that obviously you have to keep in mind if you want to do it also in the black hole situations. Now, in black hole situations, using this vector field is not a very good idea because of the trapping. In the trapping region, this will have sort of a very unpleasant effect because you have powers of t and that sort of can, in some cases, can be finessed. But in any case, it's better to avoid it. And of course, there is, fortunately, we have this new approach of Fermat-Rodniansky, which avoids it by sort of a very simple philosophy. The philosophy is that you first prove local energy decay, and then you combine with the local energy decay. Once you have it, you can use other vector fields. You don't have to be restricted to vector fields like this. And it's what they call this R-weighted or P-weighted. How do you call it? P-weighted or R-weighted? RP-weighted. OK, RP-weighted estimates. But these RP-weighted estimates, I should say, are a little bit different from what you get by the Moravec estimate in the sense that what they do, so this is what they do in Kerr or Schwarzschild. They integrate in regions like this, which are bounded between a space-like portion and the null portion. Okay? So, and of course, here you get something which is actually OK even on sigma t. And that's what we want to do. So this will be, so there are two major things that we achieved in the next result that I'm going to mention in a second. First of all, is to get the local decay estimate, even though you have this source term, right? So it turns out that if A is sufficiently small, you can still deal with that. And the second thing that we do is that somehow we take a twist over what the Fermat-Rodniansky's approach is. And we show, in fact, that you can actually prove a local decay estimates, which incorporates also this RP-weighted estimates of the Fermat-Rodniansky. So let me now go through it. How much time do I have? Well, I'm good, right? OK, good. All right, so this is theorem number 2. So theorem number 2 is you can define an adapted version of the outgoing energy on sigma t. So unlike Dafermos-Rodniansky, which go to null, you do it on space-like hypersurfaces directly. This is, by the way, not so important. The fact that you can do it on space-like hypersurfaces rather than null, it's just a technical thing, which you might or might not like. The important thing is, of course, that you can do all your estimates in a way which is consistent with these new linearized equations. In other words, you deal with the problem of the source. All right, so this is, so we can define an adapted version of the outgoing energy for our linear system and shows that it decays like O t to the minus 2 plus something, provided that A over M is sufficiently small. So what are the main ideas? We combine the method of simultaneous estimates of Marzuola, Melcraft, Tataru, and Tohananu, which by itself was a way of combining the redshift estimate of Dafermos-Rodniansky with decay, the usual decay due to the trapping. Sorry, this one? So we'll discuss it. We'll discuss it later. I'll explain. What is their method, you mean? This one? Right, well, I'll explain to you. It will be a private communication. So with R-weighted estimates of Dafermos-Rodniansky, to get a simultaneous estimate, which is an estimate. So instead of doing a separate estimate for the trapping region, in other words, a separate estimate for local decay, and another one which is this one, you do it together. Okay, so the main issue, as I mentioned earlier, is the fact that you have the presence of J in the identity d mu q mu nu is equal to J nu. So that's the only really interesting thing. The other ones are just technical. And we show that the outgoing energy decays like t to the minus 2 minus alpha. So you lose a little bit, you lose an alpha, but in the end you get, I guess everybody gets this loss. All right, so in the remaining 15 minutes, I'll just go through some more technical things. Okay? So you do what everybody does. You introduce new coordinates which are adapted near the horizon, right? So that you don't have the usual degeneracy at the horizon. So in these coordinates, the metric is smooth beyond the horizon. So these are what you do is you introduce this u plus and phi plus, which are defined as being t plus a function of r, phi plus a function of r. And the functions are defined simply in this fashion, where you choose chi to be concentrated near the horizon. All right. And in these coordinates, the metric is smooth. Of course, d3. So if you look at d1, which is partial derivative with respect to x1, partial derivative with respect to x2, x3, x4. So d3 is partial derivative with respect to u plus. It's exactly the t vector field, in other words, the Koenig vector field. And of course, you have to introduce a function space, which is adapted to this boundary condition. It has to take into account these conditions on the axis. So this simply says that phi is in H1 on sigma t. In other words, again, you have the usual picture of so the horizon here, and then transversal to the horizon, you have sigma t's going like this. Right? So on sigma t, you have this function space with a boundary condition on the axis, which is defined like this. It's psi divided by sine of theta should be in L2. Okay, so now you define the outgoing energy. So the outgoing energy will mimic the outgoing energy in Minkowski space. You take d1, so this again d1 refers to d theta. So you have d1 phi divided by r squared. L phi is this outgoing vector field, which you define like this now. So d2 will be dr. So this is a d over dr plus r divided by r minus 2m times times dt. So this would be like dt in Minkowski space. And so you see you get these terms, you get this one, plus a lower order terms, which is phi squared over r squared. So this corresponds to the outgoing energy for the phi. And similarly, you have an outgoing energy for the psi, which is defined again sort of mimicking what happens in Minkowski space, but of course there are modifications which are due to the context. Anyway, so here is the main theorem. If A is between 0 and a small fraction of m, so this is where you have to use the fact that A is small. I mean, so I think this is just technical. I think one should be able to get rid of it. But anyway, this is what we can prove so far. You pick up a constant C0, which is a little smaller than R, which corresponds. So the R, which corresponds to the horizon. So RH is exactly the R of the horizon. So C0 is between this and this. You pick functions which are defined like this. So these are the functional spaces that we had before. So this is for k between 0 and 1. So by the way, these estimates, the estimates that I'm presenting here are only for the low derivatives, in other words, for just the energy. Of course, in order to prove uniform decay estimates, you'll have to go much further. You have to take higher derivatives, which we believe that is just technical. There is no more fundamental issue involved. So you also assume, of course, that phi and psi are axially symmetric. Okay, so there are solutions of the system. And then for every alpha between 0 and 2, and t1 less than t2, and in the interval 0 t, we show that the bulk integral, so this is the usual bulk, which we'll discuss it in a second, plus an integral on sigma t2 of this outgoing energy. So r to the alpha, so again, alpha is between 0 and 2. R to the alpha. So R to the alpha corresponds to this RP weighted estimates of the framework, R alpha weighted estimates. But excuse me, but they are exactly. So we are just simply sort of combining them somehow together with local decay estimates in a simultaneous estimate. And so this is less than whatever the same kind of thing at time t1. Plus something which involves a nonlinearity. So if you want later on to do the full nonlinear thing, you also have to take into account this. Otherwise, you can assume that this is 0. So for the linearized equations, you can take this to be 0. And now the bulk is, so the bulk looks like this. You have R to the alpha divided by M to the alpha. R minus R star, so this is where degeneracy occurs. And you have, so this is the usual thing. You have a degeneracy at R equals R star, where you have the trapping. And you have all these other terms, which right. So as you know, every time you have to prove such an estimate, it's a lot of work. In particular, because you have to deal with the lower order terms. Usually the higher derivative terms, so these sort of things are not so difficult to get. It corresponds to high frequency waves, and so the trapping is very natural in that context. But typically, the main difficulty is to deal with the lower order terms, and in particular, you have to deal now with the lower order terms when you also have the source on the right-hand side. So that's what. So how do you do that? Well, you take divergence identities. Again, you assume for a moment that the linear part, the nonlinear part is 0. So you just look at the linear equations. You take divergences of P, you construct this P. So this is sort of a very universal type of method that everybody is using. You take given a vector field, a function W, and then also two other functions M and M prime. You can construct this quantity, which verifies a divergence. So the divergence, so you can do this in general. You can do a calculation in general. Okay, so this is divergence of P for any vector field, and for every choices of W and M will look like this. And then you have to adjust your choices of X and W and M and M prime such that you get a good estimate. Okay, so of course, the E's, the M, and the Q are defined like this, right? So this is what we had before. So you see it's very complicated, right? So everything here, if you want to write down in full detail, is rather complicated. But if you organize things well, it turns out that, yeah, so here is the J. And because of the fact that J is singular at theta equal to 0, that leads to all sorts of difficulties. Anyway, you have to somehow deal with this term, and you can do it by making another modification of the P. In other words, whatever choices you have to make here for the wave equation in Kerr, you now have to do this additional subtraction here, and this seems to work out well, at least for small a's. So this is what the divergence will look like after you have done this. That's not, I guess, that's not it's going to tell you too much. We use 4 multipliers: xj, wj, mj, and mj prime. Okay, so in other words, for every somehow you can think of every j indexing a particular region. So you need a multiplier adapted to the trapping region, where we use exactly the choices made by these people. So in that sense, this maybe answer your question, Michalis. That's what I mean. I mean, we just use their choices. So this is exactly using their choices without modification, essentially. A multiplier adapted to the horizon R equal RH, similar to this, but based, of course, on the redshift. So what they did was to incorporate the redshift vector field of Dafermos-Rodniansky, and that's exactly what we do, following again the Mazzuola, Metcalfe, Taratokoneanu. A new multiplier close to the trapping region, R between R star and 4M. So this is sort of the main new thing, that you have to deal with that region, and you have to be lucky to have things work out for you, and they do. And then you have to do this, we do this additional thing, which has to do with infinity now, where because we want to get this outgoing energy to decay, I mean, you want to get this R-weighted outgoing energy to decay, we have to make additional modifications. So you have to make additional choices of this. So this would be corresponding to X4, W4, M4, M prime 4. And you put everything together. But the nice thing is that you can separate. You can see exactly in every region what you have to do. You separate it correctly, and then you sort of course, each choice depends on the other one somehow, because there is no estimate. None of the vector fields here will give you an estimate that you can count on. You have to always combine with all the others. And well, I think I'm even going to finish before time, right? So it should make you happy. All right. Okay, so that's it.